Power system stabilization refers to maintaining the balance and stability of the electrical grid, especially during disturbances. It involves various control mechanisms and devices to ensure that the system can quickly return to a steady state after a disturbance. Stability can be categorized into three types: steady state stability, the system's ability to return to equilibrium after small disturbances, such as minor load changes. Transient stability, the system's ability to remain stable after significant disturbances, like faults or sudden load changes. Dynamic stability, the system's ability to maintain stability over time under varying operating conditions. Power system stabilization involves maintaining the balance and stability of the electrical grid, particularly during disturbances, ensuring the continuous and reliable delivery of electricity. This is crucial for preventing blackouts, equipment damage, and maintaining the overall health of the power system. Various control mechanisms and devices, such as automatic voltage regulators, power system stabilizers, and reactive power compensators, play a role in achieving this stability. Types of stability: steady state stability. This refers to the power system's ability to return to a state of equilibrium after experiencing small, gradual disturbances, such as minor changes in load or generation. Steady state stability ensures that the system can handle everyday fluctuations without causing significant disruptions. Example: if a small load is added or removed from the system, steady state stability ensures that the system can adjust and return to normal operation smoothly. Transient stability. This type of stability refers to the system's ability to remain stable following major disturbances, such as faults, sudden load changes, or generator outages. It focuses on the system's short-term response immediately after the disturbance. Transient stability is crucial for preventing cascading failures and large-scale blackouts. Example: during a severe fault, the system must be able to withstand the initial shock and prevent widespread instability. Dynamic stability. Dynamic stability pertains to the power system's ability to maintain stability over time, under varying operating conditions and continuous minor disturbances. It ensures the long-term stability and reliability of the power system by continuously adapting to changing conditions. Example: dynamic stability involves dealing with continual fluctuations in load and generation, such as those caused by renewable energy sources like wind and solar power, which can vary significantly over time. Control mechanisms and devices for stability are automatic voltage regulators (AVRs). AVRs maintain the voltage levels within the desired range by adjusting the excitation of generators. Power system stabilizers (PSS) help dampen power oscillations and enhance the damping of the system, improving both transient and dynamic stability. Reactive power compensators, devices such as synchronous condensers and shunt reactors manage reactive power flow to maintain voltage stability. By employing these mechanisms and understanding the different types of stability, power system operators can ensure the grid remains stable and resilient under a variety of conditions, thereby safeguarding the reliability and efficiency of the electrical power supply. Let us discuss synchronous condensers, which are essentially synchronous motors that run without mechanical load. They provide reactive power VARs to the grid, which helps in voltage control and stabilization. Here are some key points. Reactive power support. They can generate or absorb reactive power as needed, helping to maintain voltage levels within the desired range. Inertia contribution. They provide inertia to the grid, which helps in stabilizing frequency fluctuations, especially with the increasing penetration of renewable energy sources. The amount of reactive power they provide can be continuously adjusted, making them versatile for various grid conditions. Synchronous condensers are devices that function similarly to synchronous motors but operate without a mechanical load. Their primary purpose is to manage reactive power VARs within the electrical grid, which is crucial for voltage control and stabilization. Reactive power support. Synchronous condensers can both generate and absorb reactive power. Reactive power is needed to maintain voltage levels within the grid, ensuring that the voltage stays within the desired range. This capability helps to stabilize the voltage, which is essential for the smooth operation of electrical equipment and the overall reliability of the power system. Inertia contribution. These devices provide inertia to the grid. Inertia refers to the resistance against sudden changes in frequency. This is particularly important as the grid incorporates more renewable energy sources, which typically have lower inertia. The inertia from synchronous condensers helps stabilize frequency fluctuations, maintaining the balance between power supply and demand. The amount of reactive power that synchronous condensers can provide is adjustable. This adjustability makes them highly versatile and adaptable to various grid conditions, allowing them to respond effectively to changing demands and disturbances. By incorporating synchronous condensers, power systems can enhance voltage control, improve frequency stability, and adapt to the dynamic nature of modern electrical grids. A synchronous condenser consists of a stator stationary part and a rotor rotating part, much like a traditional generator. However, it runs without any mechanical load. The rotor is connected to the grid through an automatic voltage regulator AVR that controls the excitation system, allowing for precise control over the reactive power output. During operation, the synchronous condenser's excitation system is adjusted to either absorb or generate reactive power as needed. When the system voltage is low, the condenser generates reactive power to boost the voltage. Conversely, when the system voltage is high, it absorbs reactive power to lower the voltage. Synchronous condensers are particularly useful in grids with a high penetration of renewable energy sources. They are installed at strategic locations within the grid to provide localized reactive power support, enhance voltage stability, and improve overall grid resilience. Unlike static devices, synchronous condensers provide both reactive power and inertia. This dual capability makes them more effective in addressing the challenges posed by the increasing use of renewable energy sources, which typically do not contribute to system inertia. By providing both reactive power and inertia, synchronous condensers play a pivotal role in modern power systems, helping to maintain voltage stability, manage frequency fluctuations, and ensure the reliable operation of the grid. Their ability to dynamically adjust to changing conditions makes them indispensable in the evolving landscape of power generation and distribution. Shunt reactors are inductive devices that absorb reactive power from the grid. They are primarily used to control voltage levels, especially in long transmission lines in areas with low load demand. They help in reducing overvoltage conditions by absorbing excess reactive power, which is particularly useful in lightly loaded transmission lines. By controlling voltage levels, they contribute to the overall stability of the power system. They are generally more cost-effective compared to other reactive power compensation devices for specific applications. Shunt reactors are inductive devices that play a crucial role in the electrical grid by managing reactive power. They are connected in parallel shunt with transmission lines and work by absorbing reactive power from the grid. Shunt reactors absorb excess reactive power from the grid. Reactive power, unlike active power, does not perform useful work but is necessary for maintaining voltage levels. By absorbing reactive power, shunt reactors help reduce overvoltage conditions, which are common in lightly loaded transmission lines. Overvoltage can cause insulation breakdown and other issues, so controlling it is vital for grid stability. By controlling and managing voltage levels, shunt reactors contribute significantly to the overall stability of the power system. Voltage stability is crucial for the reliable operation of the power grid. Proper voltage levels ensure that all electrical equipment operates within its design parameters, preventing damage and maintaining system reliability. Shunt reactors are generally more cost-effective than other reactive power compensation devices, like synchronous condensers or static VAR compensators, for specific applications. Their cost-effectiveness makes them a preferred choice for managing reactive power, especially in long transmission lines where overvoltage is a frequent issue. They provide a simple and economical solution to prevent voltage rise without the need for more complex equipment. When the voltage in a transmission line rises above a certain level, the shunt reactor absorbs the excess reactive power, thereby lowering the voltage to acceptable levels. This process helps to keep the voltage within the desired range, preventing potential overvoltage damage. Shunt reactors are widely used in long transmission lines, especially those that are lightly loaded, as these lines are more prone to overvoltage conditions. They are also used in areas with fluctuating load demands to stabilize the voltage. By absorbing reactive power and controlling voltage levels, shunt reactors ensure the stability and reliability of the power system. Their cost-effectiveness and efficiency make them an essential component in modern electrical grids, particularly in applications where voltage control is critical. Synchronous condensers versus shunt reactors are both crucial components used to stabilize power systems, but they serve different functions and have distinct advantages and applications. Synchronous condensers are essentially synchronous motors running without mechanical load. They provide reactive power VARs to the grid and contribute inertia, aiding both voltage control and frequency stabilization. They can generate or absorb reactive power as needed, helping to maintain voltage levels within the desired range. They provide inertia to the power system, which is vital for stabilizing frequency fluctuations, particularly in grids with high renewable energy penetration. The amount of reactive power they provide can be continuously adjusted by varying the field excitation, making them highly adaptable to varying grid conditions. Ideal for grids with significant renewable energy sources, where dynamic reactive power support and inertia are necessary to compensate for the intermittent nature of renewables. Shunt reactors are inductive devices primarily used to absorb reactive power from the grid. Their main role is to control voltage levels, especially in long transmission lines where overvoltage can be an issue. They help reduce overvoltage conditions by absorbing excess reactive power, which is particularly beneficial in lightly loaded transmission lines. By managing voltage levels, they contribute to the overall steady-state stability of the power system, though they do not provide dynamic reactive power support. Generally more cost-effective for specific applications compared to other reactive power compensation devices, making them a practical choice for voltage control in long transmission lines. Commonly used in long transmission lines in areas with low load demand to prevent excessive voltage rise and ensure voltage stability. Dynamic versus steady-state control offer dynamic reactive power support and contribute to both voltage and frequency stabilization, making them versatile and essential for modern grids with high renewable energy penetration. Primarily provide steady-state voltage control by absorbing reactive power, making them ideal for managing overvoltage conditions in long transmission lines but less effective for dynamic stabilization. Contribute to system inertia, helping to stabilize frequency fluctuations and improve transient stability. Do not contribute to system inertia, focusing solely on reactive power absorption for voltage control. Highly flexible with adjustable reactive power output, suitable for various grid conditions and dynamic needs. Limited in flexibility, typically fixed devices with on-off switching capability for voltage control. Conclusion: while both synchronous condensers and shunt reactors play vital roles in power system stabilization, their applications and functions differ. Synchronous condensers provide dynamic reactive power support and inertia, making them more versatile for power system stabilization, especially in renewable-heavy grids. Shunt reactors, on the other hand, are cost-effective solutions for steady-state voltage control in long transmission lines in areas with low load demand. Choosing between them depends on the specific needs of the power system, considering factors like grid stability, renewable energy integration, and cost-effectiveness.